he's also affiliated with the Army Research Labs, and Dr. Weston is the chief scientist in math and information science in the U.S. Army Research Office. He's been there since '99, and he's been working a lot in fractal physics. In fact, over lunch I discovered that he was a student of one of my heroes, whose book I read when I was studying statistical physics, and Dr. Mantrol.
Yeah.
And so he's published, he's recently published a book accessible to everyone, where medicine went wrong, and where he basically talks about the wrong assumption of assuming Gaussian models everywhere, like we do. It's wrong to assume that, and he can tell you, you know, and he's got a lot of stories to tell you about how wrong we can be. And it's a pleasure to have you. Thank you, and the floor is yours.
Thank you very much. It's very nice to be here. How do I progress the overhead?
Okay. I think you can either do it through the mouse, or you can also do it here.
Oh.
This is the backward.
What's that?
You're pointing it backward.
Okay. Good. Here. Oh, here. Right. Double click.
I'll use the
There
mouse.
you go. I think the mouse might be.
Yes, the much more certain. Well, I guess I'll just have to stay close to the chair. Okay, what I want to talk about today is a modeling strategy. What happens when, or how you go about modeling phenomenon from simple descriptions that people use to model, say, stochastic processes, to include more and more complexity into the system that you're analyzing, and how you formally introduce that complexity and why you have to do it, how it is manifest in the data that you look at that forces you to generalize the models of the world that you develop. And so this is the outline of the talk. I'm going to start out by talking a little history. I like history. And in physics, when you talk about complexity, when you get away from field theories, the way in which complexity was first understood was by means of statistical analysis. And so how statistics entered into the description of physics, and actually started back with Gauss, turn of the 19th century, and the Gaussian distribution, and I'll talk about that and how it's characterized. And it's true for relatively simple systems. And then I want to discuss what happens as systems become more complex, and you have to abandon the Gauss distribution because you encounter phenomenon that don't have central moments. What happens when you have a process whose second moment diverges, or you have a process whose first moment diverges? So you can't talk about an average value. Can you characterize that kind of process? You certainly can't characterize it using the techniques that you learn about in statistics classes, or at least the most elementary statistics classes. All of these central moment properties diverge. And so what is it that you can say about such processes? And what we'll find is that there's a generalization of the central limit theorem that grew out of Gauss's work in looking at celestial mechanics into work that Paul Lévy did in the 30s, the 20s and 30s and 40s on distributions and a generalized central limit theorem in distributions that don't have second moments and may not even have first moments. One of the key ingredients of these kinds of Lévy distributions is that if you look at...
You can't touch it with your finger. You can touch it with a pen, but not your finger.
Okay.
Because if you touch it with a finger, it moves.
If you look at the extreme values out here where Gaussian distribution is essentially 0, these decay very slowly. They're called heavy-tailed distributions. And if you look on a graph of the log of the probability density versus the log of the variable, you in fact get inverse power laws, which were first introduced by Pareto. And this means that what happens out here in the extremes, what would be called outliers, if you have a Gaussian mentality, in fact may dominate the process that you're looking at. And I'll talk about that. I'll talk about fractal dimensions and the fractional calculus, and I'll give some examples from physiology on the practical applications of these ideas. It worked before. That works. Pardon?
Intention is very important.
Yes. Okay, so that there were two parallel paths that developed in the modeling of these phenomena in physics. I'll call this the Newtonian branch, and it started with random walks in 1905, in which it's a kind of thing that rarely happens today. A biostatistician wrote a letter to Nature and said, I have this problem. And the way you characterize the problem is that you have a walker who takes a step of length L and then rotates through an arbitrary angle, takes another step of length L, rotates through an arbitrary angle. He says, I can do it for the first couple of steps, but after that, I get bogged down. Does anyone know the analytic solution to this problem? And Lord Rayleigh, in the next paper, said, I can answer the question. He raised his hand and said, I was working in this problem in acoustics, and if you look at the problem this way, that you have isoperiodic waves and you put in a random phase, it's the same problem, and this is the distribution that you get, which of course was the Rayleigh distribution, which is the two-dimensional version of the Gaussian distribution. So this is where the notion random walks came from, is from this Pearson's specification of the problem in terms of this random walker. And then this was used as a description of classical diffusion in 1905. And the Newton's equations version of that, which was developed by Langevin a decade later, led to stochastic differential equations. And the alternative view of this process is the equation of evolution for the probability density in the phase space, which is the Fokker-Planck equation. All these lead to Gaussian statistics, the normal distribution, and a mean squared variance, or a mean squared value for the process x of t that grows linearly in time. All of that's well understood, and that's the traditional mantra that you learn in any physics curriculum and most engineering curriculum when you study statistics. Mandelbrot had a different take, as he does about most everything. And he generalized some of these ideas, and he used pieces of information that he got from other people, including what happens in random walks when it's a fractional random walk. And I'll tell you what that is a little bit later. And that was developed around 81. And the notion of anomalous diffusion, which was a mean square value that doesn't grow linearly in time, but grows as some power other than 1 in time. What if physical processes and what stochastic processes describe these? And then that leads, the description of this leads to the fractional Langevin equation, and this should be 83, not 63, and the fractional diffusion equation, and the generalization of the Langevin equation having to do with Lévy statistics and anomalous diffusion, and all of these things described in this way. So we have. And what we're going to follow is of course, we're actually going to do a little bit of both. And so we'll start with the simplest statistical models and talk about the importance of scaling, random walks, Langevin equation, Fokker-Planck equation. And I'll go through this fairly quickly as just to remind you of what's usually done. And then I'll get into the more recent work and how that differs from what's traditionally taught. But first I want to mention the importance of scaling in these kinds of processes. And so what I'm going to talk about is a kind of process where you make some measurements. All right, so say you make a set of measurements, zeta I, and then you do a sum over zeta I. So we're going to call x a diffusive variable because you're just summing up all of these terms. And if this is a Gaussian random variable, delta correlated in the time index I, the mean squared value of this is going to go like t, but we're interested when that goes to some power other than t. But we're going to call all of these a diffusive process, and the way you measure it is here you have a standard deviation analysis, which just means you look at the variance, and that goes as t to the h, where h is when h is equal to 1, classical diffusion, h different from 1, differs from classical diffusion. So that's one way to take empirical data and find out whether it obeys classical diffusion process or not. But that's not the only scaling index, because you can have a distribution function, p the variable, and time that scales in this way. Classical diffusion would have delta equal to a half. If you look at a Gaussian distribution that spreads in time with t, you'll get this kind of scaling, but this is much more general. And if you calculate the entropy for this process using this Shannon entropy definition, what in fact you find is that this quantity, s of t versus log of t, will have a slope delta. And so this gives you a second independent way of determining a scaling parameter. And when you have a simple phenomenon, the scaling index you measure with the second moment and the scaling index you measure with the entropy are the same. However, in general, they're not the same. And that's the kind of complex phenomenon that we're going to be interested in. Went backwards. Okay, so this is how you model a simple random walk. You start out, no memory in the process, x sub, no, it didn't change.
You can use a pen if you want to write on the board.
Well, okay. Okay, you start out here, you have a step at time j minus 1, and b is some operator that just changes the time index by 1. So a formal way of writing the process over there is just 1 minus b operating on x, and zeta j is the size of the jump. And so this is a simple random walk process. You step either to the right or to the left. The process that's driving the system is delta correlated. It has a strength d. You sum up these quantities. This is your random walk variable, and you do the second moment for this kind of noise. You get classical diffusion. These are what the trajectories look like. You start out, your data looks like that. You do the sum on the data. For each realization of the data set, you get one of these trajectories. And then you do an ensemble of these things. So you get an ensemble of trajectories, and this probability density gives you the distribution of the ensemble of trajectories. And so all of this is well known, and you find out when you do this analysis that you get h equals delta equals a half. And so you understand this process completely. Oh, for the days when you had plastic overheads and you could write on it. Okay, so that's the random walk description of this diffusive process. This is what the physical problem looks like. This is a picture of what Perrin recorded looking through his microscope of a pollen mote in water. And these the straight line segments are not actually straight line segments. They're the distance the particle has traveled from one observation to the next. And actually there's a wiggly trajectory in each of those straight line segments, which he didn't record. But this is sort of what the path of the pollen mote looked like. And Langevin wrote this down from Newton's law. This is the force operating on the particle. This is the random force due to the impinging of all the particles in the fluid on that one heavy particle that you're looking at, causing it to move in this erratic way. And this is the Stokes drag operating on this pollen mote that produces the dissipation to the fluid. So these are all the forces acting on the particle of interest to give it this trajectory. And then the equivalent description, you go from the dynamics to what happens in the phase space to the system and how the corresponding probability distribution evolves. And it has the same pieces. It has the piece that's diffusive, that is the force of strength D, and it has the piece that's dissipative, that's due to this Stokes drag operating on the system. And you solve this equation of motion. This is one of the few cases that you can solve it analytically. You get a Gaussian distribution for the velocity of the particle in terms of a variance that depends on time. And you see from the time dependence that if for times very... I could get annoyed with this. For times that are very short, the variance grows linearly in time. For times that are very long, the exponential kills off that term and you have a constant term. And that's essentially what this exponential relaxation says. So that's the continuum limit for the simple random walk. And now that's what you know about statistics from physics. Simple physical processes are characterized by these descriptions in terms of random walks, Langevin equation, Fokker-Planck equations. Those aren't the systems we're going to be concerned with. The system we're going to be concerned with are complex, what I call complex systems. And in complex systems, everything is an inverse power law. Vilfredo Pareto was an engineer, graduated with honors from University of Torino, and he worked as on railroads in design until his father died when he was in his mid-40s. He had a midlife crisis and became a university professor at the University of Lausanne in economics and political science. But because of his background in engineering, he said, you have to, this is 1880, 1890. And so there was a lot of social upheaval in Europe. There were a lot of political theories that were being developed. He said, well, you really can't understand society unless you have data. And so what he did is he obtained data for the distribution of income for cities in Peru, England, city-states in Italy, a number in Europe, and he found they had a universal form. The distribution of income had a universal form. And it turned out this is the log of the level of income versus the log of the number of people that have that income. It's an inverse power law. This happens to be the United States circa 1918. Then you had a number of people applying these same kinds of ideas to other phenomena. Auerbach applied it to the size of cities. This is the rank order of cities. The largest city, and then the second largest city, the number of people, number of cities that have that rank, and this leads to inverse power law distributions from 1780, when you had primarily an agrarian society in the United States, to 1930, we had primarily an industrial society in the United States. And yet, they parallel each other, but they're all inverse power laws. Because the underlying system is complex. In the same way here, because the economics was complex. Willis's law looks at you take a plot of ground and you look for, say, beetles in different areas in the plot of ground, and you look for the number of species that are within a given genre. And you get an inverse power law. If you look at language, as Ziff did, this is from Finnegan's Wake, the frequency of the use of words in language, thus the most frequent, of is the next most frequent, turns out to be inverse power law. All Western languages have this inverse power law character. What distinguishes one from the other is the slope changes a little bit. Hopi Indian language also has inverse power law behavior. You look at physiology. The size of airways in the lung is inverse power law. It has a little modulation, but it's primarily inverse power law. The internet, number of connections, number of connections to a router versus the number of routers that have that connection is inverse power law. Learning, psychology, trial and error, the number of trials you have to undergo before you have a certain level of competency, inverse power law. You can go on and on and on. The one I like the best here is, I was mentioning to Hamid earlier, this is scientific publications. This is the number of scientists that have a number of citations to their paper, because this is something that's near and dear to an academic, right? It's how you get promoted, how you get tenure. And so you look at this inverse power law, and the average number of citations is 3.2 per year, right? So if you've got 3.2 or 3 or 4 citations, say, yeah, you're average. Think about what that means, though. 35%, the first 35% of papers published have no citations. The next 49% of papers published have 1 citation. By the time you get out to the average, you've exhausted 96% of the population. So if you've got the average number of citations, you're in the 4th percentile. You're truly exceptional. Now you think about, you contrast that to the Gaussian view. When you've got the average, you're sort of in the middle. Same number below you, same number above you. If you're in an inverse power law world, that ain't true. So the mechanism, the underlying mechanism that governs this process, when you have a Gaussian worldview that's simple versus an inverse power law worldview that's complex, just totally different. So this is Gauss versus Pareto, right? In Gaussian's worldview, you had a simple science. You had a linear additive process. The output is proportional to the input. Simple rules yield simple results. Newton's laws work. The world is stable. It's predictive. It's quantitative. And you have a normal distribution. And everything is good. The world is fair. And now you have the complex scientific worldview. It's nonlinear. Small changes may lead to divergences, chaos theory. Things are multiplicative. They're not additive. You know, it's the time that you come home 10 minutes late and your wife yells at you, completely out of proportion to what you did, and you don't know why. It's a multiplicative process. It's not additive. Doesn't matter how many days you came home on time.
That was exponential.
Multiplicative. Simple rules yield complex results. A simple logistic equation, which is just a mapping, one-dimensional, leads to chaos. An unpredictable process. Things are unstable. They have limited predictability. Qualitative is at least as important as quantitative. And the inverse power law distributions rule. And this goes back to the comment I made about the Darwin quote, is that the reason I put down my books is it's not just being egocentric, it's to indicate that I've at least thought about these things for a long time, long enough to write a book about them, or 2, or 3. Okay, this highlights formally the distinction between a Gaussian distribution and an inverse power law, or Pareto distribution, with 2 simple differential equations, or Langevin equations. This is a Langevin equation. There should be a minus sign here. It should be dissipative, and it has additive fluctuations. From this, you can construct the Fokker-Planck equation. From the Fokker-Planck equation, you immediately get a solution that's a Gaussian distribution. Now, you go from here to here, and they look almost the same. The difference is the fluctuation here is in a coefficient. So here you have a fluctuation can go up or down, and it sort of has the same effect on the dynamic response. Here, it depends on where you are in the dynamic range of the variable. If the variable is small, it attenuates large fluctuations. If the variable is large, it amplifies small fluctuations. So the response of this system is very different from the response of this system. And when you go through the analysis, you in fact get the Pareto distribution. So the Pareto distribution is fundamentally different because it's a multiplicative process as opposed to the Gaussian distribution, which is an additive process. Okay, so in modern jargon, I would refer to the inverse power law distributions of Pareto as being fractal stochastic processes, right? And so the question is, how do we handle the dynamics of fractal processes? Fractals have been around since Benoit Mandelbrot introduced them in the early 80s. I was fortunate enough to be a graduate student at the University of Rochester, and Elliot Montroll had the Einstein Chair of Physics there. And Elliot had been vice president for research at IBM, and so was very good friends with Benoit Mandelbrot. And so Mandelbrot used to come in when I was a graduate student at least twice a year and give seminars. And I remember one of them was Auber's paradox. It goes something like this: if the distribution of stars in the heaven were uniform, why isn't the night sky uniformly illuminated? Why does it get dark at night? If the stars were uniformly distributed, you should have a uniform glow of light at night. Why doesn't that happen? Well, as a graduate student, those sort of interesting things to talk about. Those are the kind of seminars that Mandelbrot used to give when I was a graduate student. So I got interested early on in these kinds of things. But when fractals caught on as being fashionable, you found people looking all over. This is a fractal object, this is a fractal process, this is a fractal, that's a fractal. But there was no, after a while you say, well, yeah, pretty much everything's a fractal. What can you do with it? And part of the problem is because it was a descriptive term, no one understood the dynamics of it. If you have a fractal process, the first thing you learn, it's described by a fractal function. It's not an analytic function. You take its derivative, the function diverges. If the function diverges, you can't write down an equation of motion. If you can't write down an equation of motion, how do you describe the dynamics? Right? So you're sort of at an impasse. So what I want to talk about is how you handle the dynamics of these kind of processes, which I've just asserted are ubiquitous, because they're all inverse power law. Okay, so I want to now introduce you to more complex statistical models through fractional random walks, fractional Langevin equations, and these are in fact the ways you describe the evolution of fractal phenomenon, is through these fractional dynamical processes. Oops. Okay, so now we generalize the simple random walk. And what we'll do is we'll take what was the random walk process when alpha is equal to 1, and now alpha is not equal to 1. So what happens? You have 1 minus b, which is an operator, because b is a shift operator. And you now have alpha, which is non-integer. What does that mean? How do you interpret that object? Well, this fellow named Hosking, who was an economist, said, well, the way you interpret it is you take the inverse, you multiply the left by that object with to the minus alpha, and so you operate on zeta j with that object to the minus alpha. And since you have something to the minus alpha, it's two objects, the thing you immediately want to do is do a binomial expansion. You do a binomial expansion and you can prove, you do analytic continuation in the complex plane, and you go through all the standard traditional analysis, that in fact what you wind up with is an expression for the process. I didn't even touch it.
It senses you.
What were you thinking?
Yes, exactly. I'm thinking I'm not going to get so close, is what I'm thinking. All right, this object, which is the dynamical process at time j, is related to the jumps or random steps at time j minus k. But k goes from 0 to infinity, which means what's happening now is dependent on what's happened in the infinitely distant past. So by making this a fractional random walk, what I've done is I've introduced a memory into the process, so what happens in present time cannot be divorced from the history of that process. But you look at the coefficients, and these are gamma functions, so you know everything about them, they determine how strongly the past influences the present. Because you can go out as a function of k and j and alpha, and k and alpha, and what you find is that as you go farther and farther back in time, this actually becomes an inverse power law dependence on the coupling. And so when you construct the correlation function for this process, you in fact find that it depends on the time to the 2 alpha minus 1, and this would be like t. So this gives the non-integer exponent, or the non-unity exponent of the diffusion process. So you can relate this scaling behavior back to the fractional random walk. And this is an exemplar of a stochastic process that you generate on the computer that has a scaling of 0.75. This is a fractional Brownian motion, which means that it has a Gaussian statistics with this kind of correlation, so that you have e to the minus x squared over 2d t to the 2h over 2 pi t to the 2h. That's the statistical distribution for the zeta, or h is equal to 0.75 in this realization. And what you find by looking at the two methods that I mentioned, you're looking at the second moment and looking at the diffusion, that the scaling delta is equal to 0.75, which is the same as the exponent of 0.75. So this is still a simple process by my earlier definition, because both scaling exponents are the same. And that's borne out by the fact that it has a simple statistical distribution. Still Gaussian. Now I want to do the same generalization that I did before, where I went from the random walk to the Langevin equation. Actually, that's just going from a discrete version to a continuous version. So now I want to go from the fractional random walk to a continuum equivalent of a fractional random walk, which I call the fractional Langevin equation. And that equation is given here. This is the random force, and this is a fractional derivative, a d to the alpha. And here I've defined a fractional integral, which is the antiderivative, which is an integral from 0 to t over the function that you're operating on, weighted by t minus t prime to the 1 minus alpha. So what this is saying is that you have an operator, d to the alpha, operating on some function t, and that's given by a kernel t minus t prime, f of t prime dt prime, 0 to t. And the particular fractional calculus you adopt is determined by what kernel you have in there. And there are many different choices. And the one here is the Liouville-Riemann choice, which is 1 over t minus t prime to the 1 minus alpha 1 over gamma to the alpha for normalization. But what you see there is the same thing we saw in the discrete case. It's taking what's happening now and it's coupling to what's happened in the infinitely distant past, and the kernel is giving the weighting for how far of how strong the influence is from these distant pulses or random events are that are driving the process. And so you can integrate this, and you have to do the fractional calculus, and that's a good book to use if you want to do that. And I didn't tell him to bring that, but you'll do well in graduate school. Of the mean square displacement, and that gives a t to the 2h, this anomalous diffusion, and it relates the scaling index h, which is after Hurst, to the fractional derivative for the process. So this suggests that when you have a phenomenon and you look at the diffusive nature of the second moment, and it goes as t to the 2h, and h is not equal to a half, that a potential candidate to describe the dynamics for that fractal process is a fractional differential equation. All right, and this is a discussion. You can go through this in fairly general form. This is showing that if you have a fractal function, and here's a realization of a fractal function. It's called the generalized Weierstrass function. Weierstrass, the mathematician, had this fellow Cantor as a student. Cantor, who developed Cantor sets that people talk about in fractals. Anyway, he was a rather precocious student and later became a colleague. And he was interested in infinities and how to categorize infinities. And Weierstrass was a master of analysis. And so he challenged his mentor to come up with a realization of a function that was continuous everywhere and nowhere differentiable, as a realization of one of the singularities that he had been studying. And this is related to what Weierstrass came up with, which is a function that's continuous everywhere and nowhere differentiable, which means it's a non-analytic function. Right? You can't describe its evolution by taking a derivative. But you take this function and you scale time with a constant b, and what happens, you get the same function back with another constant a out in front. This is called a renormalization group relation in physics, and has a general solution of this form, where this hk is actually given by the log of a, log b, where these are the two constants, and a term that depends on I. So this is a complex fractal dimension. And the ordinary fractal dimension is 2 minus log a over log b. You take the derivative of this guy, it diverges. So this is a fractal function, right? And so, and this is the interesting thing, is that its derivative diverges. But now we want to take the Riemann-Liouville derivative of this function, or integral of this function. And what you find is that if you do this, you can show analytically that what you get is a new function. If you take the fractional derivative, the alphth derivative of this function, you'll in fact get a new fractal dimension. That's the old fractal dimension. If you take the derivative, it's greater. If you take the integral, it's less. So that you can go from one fractal function to another fractal function by taking fractional derivatives or fractional integrals. So now you have a calculus by which you could describe the way fractal functions change over time, which means you can describe evolution. This is an example of that. You start out with a process, a Wiener process. This is a random function that we're talking about. You can take its Fourier transform. These are the Fourier amplitudes. This has an autocorrelation function, delta correlated in time. You now take a fractional integral of that, and it's the same. You see what happens when you take the fractional integral using the definition that I put on the board over there. All that does is give a different weighting to these Fourier coefficients. And that weighting is to the alphth power. And you take this definition of the operation of the fractional integral on this Wiener process, and you take the second moment, and you find, in fact, that you have the Fourier transform of omega to the 2 alpha, 1 over that, and by a Tauberian theorem, you can show that that goes like the time difference to the 2 alpha minus 1. So you can say, you can represent this process as the fractional derivative of this function f alpha being driven by a Wiener process. So this is a differential, a fractional differential description of the evolution of a process being driven by white noise. And f alpha is the response of that process, and you know everything about it. Since the operator is linear, it has the same statistical distribution as the driver, and the weighting comes up in the correlation function. So it has different correlated, the noise is delta correlated in time, the response has this long time memory. So you can develop an entire calculus, and so this just summarizes all of that, that you start out with a fractal function d, you take a fractional derivative, and you get a new function d plus alpha. And so you have the beginnings of a way of describing very complex systems. So now, fractal time series. What do you do when you have data? How do you use this stuff, really? All right. An example of what you do when you have data, this is something I call Taylor's law. Taylor was a biologist. And in the early 60s, he wrote a couple of papers in which he developed a technique. And the technique was he took a field and he broke it into squares. And each of the squares he did sampling because he was looking for the number of species of a particular kind of genre of beetle. And so that each square in the field now became a realization of the number of species of that genre of beetle. And so then he had a number of realizations of that distribution, and he could calculate a second moment for the distribution. He then partitioned each of the squares into smaller squares, went through the same process again, calculated another second moment, repeated this process ad nauseum, and was able to show that the second moment changed as a function of resolution. As he got finer and finer resolution, the size of the second moment changed. So I said, well, if you can do that by refining the calculation, making things smaller and smaller, you ought to be able to do it by aggregating the calculation. Yeah, because if you scale in one direction, you have to scale in the other direction as well. So I said, well, let's take a billion or a million data points, Gaussian statistics on the computer, right? And now let's add the nearest neighbors together. So you have 500,000 data points. Well, you take the million data points, you calculate the second moment. You add the nearest neighbors together, you calculate the second moment. Go back to the original distribution, add the next 3 nearest neighbors together, calculate the second moment. This is what you get. This is the log of the variance, and this is versus the log of the mean. You get a straight line. What Taylor observed is that in general, the slope of this curve, that you get what he called the power curve, that the variance as a function of resolution, which is m, in my case, how many elements you add together, is equal to the mean to the power b. And that, and if you take the log of both sides, this is the kind of curve you get for the data, and he got that for a number of species. And it has some very interesting interpretations. If b is equal to 1, and you can see here that this has a slope unity, that things are completely random. They're independent of one another. If b is less than 1, then in fact you have something like an orchard. Things are fairly evenly distributed on the field. And if b is greater than 1, what you have are like herds of sheep or cows. You have a clumpiness associated with the distribution. So you have here a natural way of querying the data to find out what the nature of the statistics are, whether it's even, whether it's random, or whether they're correlated patches in the data. And you can show analytically that the fractal dimension is given by 2 minus b over 2 from the slope of this curve. So this gives you a handy-dandy prescription for analyzing data sets, which is nothing but aggregation and calculating the mean and variance. You use this and you can determine whether or not your data scale or whether or not it's fractal. There's a couple of other things you can do. For example, you can also prove that for these kinds of data, the correlation coefficient is 2 to the 3 minus 2d, where d is the fractal dimension minus 1. So that in the case where d is equal to 1.5, you in fact have an uncorrelated process. The correlation coefficient vanishes, and you show that this is true of Brownian motion. that you get a fractal dimension of 1.5. When d is equal to 1, you in fact get r is equal to 1, so you have a regular process. Things are absolutely correlated. So it gives you a way, and then you have a relation between h and d, so you can, if you know what h is in the second moment, you can know what d is, and you have all these different ways of interpreting the underlying process. This is applying that to physiological data sets. Whether you're talking about breathing, heart rate, body temperature, gut rumbling sounds, stride intervals, or blood flow to the brain. All of these time series are fractal. They're actually multifractal. The difference between a fractal and a multifractal is a fractal time series has all these nice scaling properties that I was talking about before, including the Taylor. A multifractal is one in which the fractal dimension doesn't remain constant through the time series, but changes with the time series. Say you look at these and you find the difference. This is a scaling property using that Taylor's law between something that's random and something that's regular. For this is heart rate. This is one of the things that's interesting. If you saw this time series and you saw this time series, you would think that they had nothing in common, just looking at the raw data. But when you do the processing of the data, you see that they both scale in the same way. Same thing here. If you look at these data, which are just, well, I should mention what the data is here. Heart rate. That's the time interval from one beat to the next beat of the heart. So that's a time interval, and you look at the next time interval, and you have a sequence of time intervals, and then that defines your data. Those are what's interconnected here to form this time series. And then you just do what I said about aggregation, and you get this behavior for the scaling behavior. This is the same thing for the time between sequential breaths in the body. That's why this is about a factor of 6 or so longer than this. These time series are, if I'm just walking along, the time interval from one heel strike to the next heel strike of the same foot. That defines a stride interval. That's determined by the motor control system. That's also an inverse power law process. Body temperature that everyone thinks is so constant has slight fractality associated with it. This is blood flow to the brain through the middle cerebral artery. Has the velocity of the blood flow has this kind of variability. And the peak here is at the fractal dimension, and this is the distribution of fractal dimensions for the multifractal property. Now these are fractal heartbeats. As I said, if a heartbeat is fractal, then you can't, the normal dynamical equations won't describe that kind of behavior. And so we developed a kind of fractional diffusion equation. This is the probability density, and this is the probability of having an interval of size x at time t, and this is its equation of evolution. And these are what the data look like, the raw data. This is constructed in histogram, and you see the data have these tails, and this solid curve here is a Gaussian distribution. And if you plot it this way, the Gaussian doesn't look so bad. I mean, it's only off out here in the tail region. How important can that be? Except now you look at the log of the relative frequency or probability distribution versus the variate. And this is a Gaussian here. These are the data. And the solid curve here is a Lévy distribution. So you see that they're distinctly different when you take into account the long time intervals in the interbeat. Well, and when you stop and think that it's the long time intervals that are important, because when they get long enough, you die. So you don't want to make them too long. So that's what you want to describe dynamically. And it turns out that this distribution has this scaling property that I mentioned before, and a fractal dimension, and asymptotically it has an inverse power law. These tails are inverse power law of the form that we were talking about. So there's an intimate connection between inverse power laws and Levy statistics and fractional derivatives. And over the past decade, couple of decades, I guess, work with Ari Goldberger. We started on this in the early 80s. This is heart rate, healthy dynamics, has a fractal dimension between 1.1 and 1.3. All right? Now, there are two ways you can change that. One is that you can increase the correlation that leads to something that's almost periodic, that you might call normal sinus rhythm. And this is congestive heart failure. And that has a D of approximately 1. Or there's another way you can change this behavior, and that you can decrease the correlation, leading to this kind of heart rate. And this is called atrial fibrillation. This patient also died. And this has a fractal dimension that's very similar to Brownian motion. So this is death by organization, and this is death by disorganization. So the lesson of this is that truly complex phenomena are a combination of regularity and randomness in some balance that maintains the integrity of the system. Either too much order or too much disorder are both fatal to physiological systems. Multifractal time series, I'll go through this quickly because it's getting late. As I said, as soon as you identify something as being fractal, you can construct a fractional equation of motion, a multifractal. You can also do the same thing. So this is the velocity of arterial blood flow, the blood flowing to your brain through the middle cerebral artery. It has this form. These are the fluctuations. This is the memory kernel. And you can solve this equation trivially by using scaling. You scale time in the kernel, and you know its functional form, 1 over t to the alpha minus 1 or whatever. Gives you a lambda to the alpha. You scale the noise, and if it's fractional Brownian motion, you know the scaling of that as well. So you know the scaling of the solution. So you never have to solve the equation. Right? You just take the moments of the left side and you take the moments of the right side, and you find that you have that you can solve this equation, including this exponent, without ever having to know what the formal solution to the equation is. And what you find is, for a multifractal distribution, you can calculate this distribution function so that this is the dots are the data and the solid line is the curve. That's a one-parameter fit to the fractional derivative representation of the solution. That's a sigma, the strength of the fluctuations. And here, this is a comparison between normals and people that have migraines. So that you have a normal range of variability in the fractal dimension for normal healthy individuals, and this curve is actually an average over 20 healthy students. And this is an average over a collection of, I think it's 13 people that are susceptible to migraines. Not while they're having the migraine, but they're susceptible to them. And what you find is a very constrained distribution, which means that the normal variability that's accessible to an individual in terms of the vascular bed and its responsiveness to blood flow, right, is constricted in a person susceptible to migraines. And that's the mechanism that causes it. And you can actually relate the severity of the migraine to the narrowness of this distribution, the loss of variability that's associated with this. And you can do the same thing to a stride interval that also turns out to be multifractal. You can go through the same kind of analysis, normal walking gait, and you get the same kind of behavior fitting to the multifractal. This is something that's sort of interesting because we developed an analytic model for the gait. There was a model called the central pattern generator, and with the true creativeness of the scientists, we called ours the super central pattern generator. And this is what happens when you take an individual, and this is a normal multifractal distribution. Then these are, at the beginning of the walk, you tell the person, walk a little faster than normal, walk a little slower than normal. And you see that simple instruction, that internal stress that you create, completely changes their response pattern. Then you do something that's externally restricted them. You put on a metronome. And you ask them at the beginning of the walk, try to key your steps to the metronome. And you've adjusted the metronome to be at their normal pace, at their slow pace, or at their fast pace. And you see that at their response to the metronome is just very different than their response from internal stress. So the way a person reacts to internal stress and external stress at the level of their neurological motor control, much less their psychological makeup, is just very different. And this is what you can compare that to what happens when you have certain kinds of neurodegenerative diseases and how the distribution changes. And there's been a lot of work in this area. And we've been able to capture these first two things in the model that we developed. What's interesting, this is a average normal gait. This is averaged over 20 individuals. And you see, when you have normal, slow, and fast gait, you can fit the averages to these distributions. It's actually, this curve is actually the distribution of multifractality gives rise to this probability distribution for the scaling exponent, right? Now what happens over here? Well, what happens over here is you put the metronome on. And there are people who just can't keep a beat. Anyone that's ever been in the military knows there's always someone who can't march in cadence. No matter what you do, no matter how you threaten them, no matter how you intimidate them, they cannot keep cadence. There's something about the way they're hardwired that they cannot respond in synchrony to what everyone else is doing. And that's evident. Well, this person who's the triangles here, right? He's here, he's here, he's here. His fractal dimension is all over the place. Whereas when he was determining whether he was walking normal, slow, or fast, he fit in right with everybody else. So there are physiological phenomena and physiological reasons why some people cannot adapt to external stress. They just don't work that way. And so they become academics. I was a professor for 10 years, so I can say that. Okay, so what can we conclude from all of this? That complex phenomenon, in the way I've defined it, is a combination of regular plus random. It has both aspects. Too much of either is fatal. And so you can't describe it by a differential equation of motion for either the dynamical variable or the probability density. So neither the Langevin equation nor the Fokker-Planck equation is an appropriate description for a complex phenomenon. And the scaling properties of a number of physiological systems, gait, heart rate, breathing, blood flow, all of these things indicate that you have an underlying fractal structure. And in some cases it's geometrical, like the architecture of the lung has been shown to be fractal, or in its statistical behavior. And the strength of all of this is that we have identifying these things as fractal is more than just identifying their structure, but allows you to construct equations of motion using the fractional calculus that can then be tested against experiment. No, that's the wrong word because we're talking about physiology. Against data. So the fractional calculus, you can describe the dynamics of any complex stochastic phenomenon. And the important thing here is that what's significant is that either the traditional treatments are inappropriate or they become so unwieldy as to be almost useless to everyone except the true expert in the area. They're almost impossible to communicate to the non-expert. Whereas I think most of this, you can describe the essential features without having a deep mathematical background. And with that, thank you very much.
Migraine correctly, a person, when they're having a migraine, they're having an arteriospasm. And am I correct in interpreting that the reason that they have the migraine is they're incapable of compensating because they can't regulate they don't have enough variability in their blood flow to compensate for the spasm. Is that correct?
It's not in the blood flow. It's the hemodynamics. It's the vascular bed does not have the vasoelastic responsivity that it needs. And you see that even when they're not having the migraine.
Yeah.
So when it goes into spasm, that just becomes more evident. I think that part of the strength of this approach is that you can see features of the pathology without the pathology being present. Right? And that makes it diagnostically valuable.
Any other questions?
Yes?
I've read of examples of simple systems which evolve with time and become complex based on certain very simple rules, like cellular automatons and things like that. So are those used for modeling in physiological?
Well, yeah, for morphogenesis, right, when things grow, for example. When the embryos form, when a human being is being formed, they're growing, for example. Why do the lungs become fractal during morphogenesis? Well, I have my explanation for why that happens. My explanation is the following. If you have an environment that has noise, right, and you have something that's growing in the environment and is responsive to the environment, then that noise is going to introduce scales into the system that's growing. It's going to perturb it in some way. Right? If you take simple systems, the kind of thing that you find is that the way the noise grows is like e to the x squared sigma. And this is with a positive sign. So that grows very rapidly, right? The error in that kind of system. But now I look at something whose growth law is inverse power law. 1 over x to the lambda, right? And now say lambda is the parameter that's being perturbed by the environment. Now, the way that this thing, the error grows for this kind of process is e to the sigma log x squared. And you look at what happens and the growth of these two curves, one grows like this and the other essentially grows like that because of the logarithm. And that the logarithm in the growth of the error is related to the inverse power law in the dynamics of the process. And the way to understand that is, this is traditional scaling. Now, the scaling in this process would be like e to the minus lambda x would lead to that kind of error. So every time you get a fluctuation, you get a new scale, right? It's introduced in the process. And so that's why the error grows so rapidly. But now you take a fractal process. Well, a fractal process doesn't have a characteristic scale. Another way of thinking about it, it has all scales. So when I introduce a fluctuation, I introduce a scale, but that scale was already present in the process. So I'm not introducing anything new. Therefore, it's not an error. And so a fractal process is pre-adapted to a complex changing environment. And so the thing, what you would associate with an error for the process, just grows very slowly.
That's where the heavy tail comes in, is that right?
Yes, that's right.
Any questions? I have a question. So has, for instance, you were talking about the use, which is actually quite interesting and intriguing, of this fractal theory to medicine. Now, has there been any use of it, for instance, where the fractal dimension can actually be used as a predictor of some disease of some kind, or it hasn't gotten to that?
Let me give you I'll give you a clinical example that's not quite that, but it's close.
Yeah.
This fellow named Alan Much, who is a physician in Winnipeg, Canada, who, after reading some of the stuff, decided, well, this should have influence on post-operative patients that are put on a ventilator. And so he said, well, he did some experiments. He traumatized pigs. And he separated the traumatized pigs into two groups. In one group, he put on normal ventilation. Another group, in the normal ventilation is you periodically drive the respirator. So you have a harmonic modulation of the lungs for airflow. The other, he recorded the normal breathing pattern of a pig for a long time, put that in a computer, and used that to drive the ventilator. He called that biological ventilation. And so he compared normal ventilation with biological ventilation and looked at all the indicators for the pigs who were recuperating. Oxygenation of the blood, different uptakes of chemicals and so on that you use as indicator for how well the pig is doing. And the biologically ventilated pigs did an order of magnitude better than the normally ventilated pigs. Last year, or a year and a half ago, he did the same thing with people. I mean, he didn't traumatize the people, but people coming out of operations. He compared the normal indicators with people that had biological ventilation with people that had normal ventilation who were post-op. Same kind of surgeries and so on, and found that there was not an order of magnitude, but significant improvement or increase in all the indicators for people that were biologically ventilated. And so this poses a philosophical question, which has to do with matching the complexity of the intervention to the complexity of the network you're intervening. And if you want to get a maximal response from the network you're intervening, you want to match the complexity with the intervention. And as a matter of fact, we developed a mathematical proof using non-Poisson renewal processes with inverse power law distributions for one system and perturbing that with another system as a function of the measure of complexity, which is the inverse power law. And the response curve is truly amazing. The response curve, if this is the slope of the curve of the perturbation in this direction, and this is the amplitude of the response of the system, and this is the sort of the value that the system curve is set at, this is what the response looks like. Look familiar? No, this is much stronger than stochastic resonance. This looks like a linear resonance curve, except it's not. It's a non-Poisson renewal process driving another non-Poisson renewal process, matching the complexity of the two systems, and it's the totality of one system responding to the totality of the other system, which looks like linear resonance. It's really intriguing stuff.
Are there any other questions? Not, let's thank our speaker again.